It's disappointing, God. Especially you'll see some funny indications of why I'd be disappointed as we go along. Also, you'll see. So last time, I claimed I could give the most important ideas in classical control in 60 minutes, and I claim I did, and hopefully you saw it on the video. But I realized, it's not enough. So I need to go through a design carefully, and a blackboard's impossible. So I started to try to do it on the computer, and I realized what I really need to do is explain to you the steps you go through on a computer to do it. So I ended up spending the entire hour on control, but looking at a particular example. So how does a grid operator know how to set the gains in their automatic generation control? So this is all going to be gearing up. And once you understand what's in their mind, you can say, hey, I've got a fuzzy logic controller that'll make my washing machine provide artificial droop, and you'll know why you get laughed at. So, you know what I mean? So what you need to understand what the grid operator really needs before you start acting like demand resources are going to do something. And that's what nobody does. Most of the people who propose smart grid demand side stuff don't know anything about control. So they, all right. So through this example, I'll go through and explain that. So look at that first time. Just one bullet. So we saw this. This is not reality, but it's a simulation of a high fidelity model of the grid, and now we're paired. So there's, depending on how much wind there is, you get different responses. So extreme means there's a high penetration of wind, so less inertia in the system. And I said, I don't remember what WEC is. I'll look it up for you next time. The Western Electricity Coordinating Council. And I won't say anything more. You can remember, underline means click, and you can read all about it. So if you have insomnia, you can go to that page and read. And I also showed you this maybe more simplistic model of Texas that was looked at by a really nice paper by Baldick et al. The effects of very fast response to frequency fluctuations. And it's a paper, actually it would be a good paper to look at for a report. And so basically they're looking at the same sort of things I'm looking at in this lecture, is that, given a grid model, what do I do with it in terms of, dealing with, controlling the grid. So let's do it. Okay? And you can click that again and get the paper. Let's do a design. So remember this awful thing. So, so for this particular paper, I pulled out one of the examples. The example is actually for this more extreme case here, where there's a very fast response time to shoot. Whether that's bad enough, we'll see. I don't know. The fact that it's so lively, so underdamped, looks scary at first, but to a control engineer, I don't know. We'll discuss that, whether this is a bad thing or not. Unfortunately, our guy from Duke's not here, because he's the one who asked this question. But anyway, so there were two transfer functions, and I don't want to review all this, but remember rho, I'm the balance. So the balancing authority is, overseeing a big region. In Florida, there are lots of little ones, like the GRU is its own balancing authority. But all of South Florida is Florida Power and Light. That's a balancing authority. Then most of northeastern U.S. and a lot of the Midwest is under PJM. So there's one control center, where they're going and making decisions for the entire fleet, for a quarter of the U.S. And they broadcast this to every single generator. Well, there's some generators that opt out of control, but any generator that will accept a control signal from the balancing authority, that's common to every generator. And then this is, I hate the notation again, those are disturbances such as variability in power from the wind or from solar, but also generator outages. Okay? So that not frequency sensitive load deviations could also be power. And so there's a zero in the transfer function. We derived that a couple lectures back, and there's no zero here. And you can approximate A by a second order polynomial. So it's a second order transfer function.
So what's A of S?
So we derived it. Was it last? No, you were there a week ago. It's I can't give it to you again, but it's there. It's, we had a B, which was the summation of the reciprocal of those group parameters. That was the summation of 1 over Ri. And D was the constant for all of these frequency-sensitive loads. And TG was the time constant for all these governors, I guess, right? And then M was this sum of all of the inertias in the system. So we derived this. And it's very hard to see what the hell that is. So you've got to look at a numerical example to figure out, is this less than 1? That's when you have underdamped response. Okay, so again, so this is a disturbance. And the main thing we'll be talking about in the next lectures is this rho, which is a command from the balancing authority. And Roberto, that was your question last time. That's going to be part of the secondary control architecture. So how do we do it? So here's the example from this ERCOT study we're going to look at in detail, where they got this disturbance transfer function here, and I'm just going to normalize this other transfer function. This is the transfer function from the command input to the frequency deviation. And I'm just normalizing it so it has DC gain unity. And I can always do that because I can always scale rho. So it's, it's irrelevant, the exact constants. So this is a case where the damping ratio is 0.6 and the natural frequency is the distance here. So when the damping ratio is less than 1, then we have this geometry. As theta being this, zeta being the sine of theta, we saw last time, and omega is the distance to the origin. All right? And so that's an underdamped system, but not very underdamped, so it's not a huge overshoot, if you look at it. And I think that's what I'll write down next. Yeah, so there it is. So this is normalized, but I've basically looked at step responses. So if you're going to do a control design, you look at various different, you get intuition from various different portraits of the system, and one is a step response. All right, and this is not. This system has unity gain. So if you put in a step input, its steady state will be unity. So I basically scaled the step input first to make it negative, so it's like an increase in load or a decrease in generation. And I also scaled it so the steady state behavior is the same as the plot I showed you before. But you see that the response to a disturbance has this big undershoot in this case, and a step from the balancing authority doesn't, and that's because this had the 0 in the left half plane, which we explained last time. It causes that more extreme behavior. Well, this doesn't. All right, so that's the first thing. You look at this and you say, well, it's underdamped, but not very much. It doesn't swing around or oscillate. It just comes down a bit. And that blue thing is the thing you use for design. That's all you care about when you do control design. So the zeros for the disturbance are important. They tell you something. But in terms of getting a control design that is stable, robust to model uncertainty, rejects disturbances in a certain bandwidth, all the goals we talked about last time, it's that blue guy. All right? All right, so that's the first thing, step response. The next thing is you look at the poles and zeros, as we did before. So this is exactly, if you actually have the damping ratio of 0.62 blah, 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 and that natural frequency, you can type in MATLAB PZ plot, and you'll get this, And there you have it, that's all. Okay, PZ plot. Well, you look it up. Okay. So the next thing you're going to do is this. You're going to go into MATLAB and you're going to start to create transfer functions. And so I want the transfer function for the disturbance, and that's defined right there. I write GPD equals transfer function, and I put in the numerator, there it is, and I put in the denominator. There's a 1, because the coefficient of S squared is 1, there's this 0.4797, and this thing here, all right? And there you get it. So MATLAB then immediately puts it in the same form that you would have done it in a math program. So that's really, I love you MATLAB. I mean, it's amazing what they did for us. Control, you can't imagine how awful it was to teach control when I started as an assistant professor and there was no computing technology. There's nothing, you know. It was, you know, you really couldn't tell the difference. You had black boxes, and nobody could tell the difference between what was a compensator, what was a plant. You know? And having this is just, it's heaven. You know? So anyway, you do the same thing for the thing you really care about. Again, this is the transfer function for the from the balancing authorities command to frequency deviation, and you get these guys, and then you can look at a Bode plot, because that is it. I mean, you need to understand a Bode plot for design. Forget anyone in power systems who goes on and on about pole zero plots. For a single input, single output system, it's crazy to look at pole zero plots. And power systems engineers do not know that. They really don't. I mean, I've been around them long enough to see they get a different education than people in other disciplines. And here's why. So basically, you're going to type Bode GP and Bode GPD. There's a hold there that's missing. You know, figure, then type hold to get two plots on the same page. And you see this resonance up here for the blue guy. The blue guy is the one with the zero. You know, so the zero creates that response like that. And for this other guy, you see it's more flat. You don't see resonance. All right? And that's the thing you have to stare at when you do design. Now, why do I dismiss pole zero plots? Because when I look at this could be a 5 million order system. It could have 5 million trillion poles and zeros. You know, but yet I wouldn't give a damn. I could do a design, you know. I mean, the complexity of my control design has nothing to do with the complexity of the system. Well, if I do a control design based on poles and zeros, I'm dead if this is complex. You know, I'm completely dead. I don't have any intuition. And the intuition you get from the Bode plot is infinite, and the intuition you get from poles and zeros is really fragile. It's just not useful at all. So actually, I have one of my students from Illinois who I used to preach about this. He actually ended up at Pacific Northwest National Labs, and he's been educating people there about not looking at that, but looking at that. So it's So anybody who's not taking control, you're allowed to whine. So tell me to slow down if I need to. Yeah? I want to whine?
That's fine so far.
Okay, cool. So here's where I sit down and get to work. First of all, I write down a Bode plot. And I gave myself a lot of room. And partly it's because last time, well, there'll be a lot of these. We're going to come back to this plot a lot over the next weeks. So it's going to be really useful to illustrate a lot of concepts. But last lecture, I designed a PI compensator, and I ended up, well, designing it so I would have good frequency rejection over here and basically nowhere else. I had high gain at frequencies down here, but not elsewhere. So we want high gain. The larger the region we have high gain in our compensator, the broader the range will have disturbance rejection. So this black diagram is going to appear again in a moment, but I just want to say it again. To reject disturbances, actually, you need this guy to be big. I said that before the disturbance in entering here, then either of these guys could be big. But there's a slight mistake there. If the disturbance enters here, for example, GC has to be big to kill that guy off. You can't align the plant. All right? So, but you can't make GC big everywhere. You make GC big in a certain bandwidth, and that's why we ended up with PI control. from last time. So PI control just means not JWS. It means you have a positive gain times 1 over S. 1 over S corresponds to integration, and then a proportional gain as well. And this is big at DC. When S equals 0, that's DC, and this is infinity. So you get very high gain at DC, and the gain tapers off, because when the frequencies get larger, S is J omega, this thing decays linearly down to 0 on a Bode plot. All right. So anyway, the first thing you do when you do a control design is you somehow get a Bode plot, and you might do it empirically. You might put sine waves into the system. So I'm the balancing authority, and I'm saying, hey, grid operators, I'm doing a test. I'm going to put in a sine wave of this frequency, and then I'm going to step up the frequency, step it up again, step it up again, watch the response on the grid, and then get a point for phase and magnitude there, get a point for phase and magnitude there, and do it for several frequencies. I might do that, you know. You do that in all sorts of applications. I'm not saying they do, but they might. After you do that, you'll look at this, a region like this where you don't know anything, you know. And actually, for like ERCOT, it's bigger than this. It's a big region where you have a lot of uncertainty in terms of phase and gain. And so you got to identify that. And that's there, you don't want high gain there. Because you don't, you know, because if you don't know much about the system, you want to suppress its behavior. Because I know 0. So if I multiply this by 0, then it's known. So in this region here, I have to worry. Here, take a look. I know that. 0 dBs and some constant. I wrote 0 there, whatever it is. That's known. So I can mess around there. And that's where I can crank up the gain. So in a control design now, once I understand the system, I'll blast up the gain there and shove down the gain there and walk away home until I do an experiment if it didn't work because I forgot about something, you know. But anyway, you know, this is, anyway, it's a first step. So, I'm scared. I didn't want to do that. All right, so let's do this. Let's do a design. Okay, I'm just writing down what I wrote down before, and I want to write down a Bode plot of a PI compensator. Okay, so it shoots down linearly. So I said this last time, but it's worth saying twice. For when S, which is J omega, is very small, this thing is huge. It completely dominates this. And you're basically looking at just integral. And a Bode plot of 1 over S, it's just minus a Bode plot of S. It just goes down linearly, minus 20 dBs per decade. If you don't know what that means, don't worry about it. And at some point it flattens out, and that point is a 0 location. And it's when this is equal to 0, you got to put this. You got to rationalize this, and so that's minus k over kp, I think. S on the top and bottom. Yep. It's when this thing is 0. I'll let you work it out. If I'm wrong, don't tell me. I don't care. It doesn't matter. There's a place where that transfer function is 0, and there it is. I know that's right. Okay, so that's a Bode plot. And the scary thing about PI compensators is right here. is that this dividing by s, forget the kp for a moment, when 1 over j omega is just minus j over omega. And so that's why the phase of minus j is minus 90 degrees. That's why you get that. And phase lag is what we worry about. Phase lag is like delay. And so that's where the phase lag here is unfortunate. We don't want this zero to interfere. We don't want this phase lag to get us into any trouble, possibly over here. Unless we've suppressed this enough, it doesn't matter. So it depends on your design. So let's just do a conservative design.
So if you suppress that enough where you would still have the phase lag, but it wouldn't have enough of an effect in your system.
Well, we can make this really precise. So it's that thing. Well, we'll have to go. I'm going to go back and review phase and gain margins in a moment. So another thing is that we're going to presume we have a stable system to begin with. Okay, and as I discussed last time, as we slowly perturb the system, the stability remains. Stability is a continuous operation. So if I have a Bode plot and I perturb it a little bit, the system is still stable. I said this last time, but I'll do it again. So stable means that my poles in the left-half plane for the overall system. For the feedback loop, that's what we need stability. Now, as I perturb this Bode plot through design, I'm going to add a PI compensator. I'm going to move this Bode plot around. The closed poles will move. They'll change around. Now, as I say, crank up some gain or move some parameter, the poles will move slowly, continuously, and the very first time I get into trouble, I'll have poles on the imaginary axis. Because of the fact that the poles move continuously. That's why the imaginary axis is so important. It's a boundary between stability and instability. Okay, so I want to make sure my poles are far away from the imaginary axis, and I'll review how do we think about that in a moment. Okay. All right. And in fact, right here. So I'm only going to do one design. I'm going to do a really conservative design. So first I'm going to note that 10 to the minus 1 radians per second I was playing around with this last night, trying to get some intuition for it. It's one cycle, one round per minute. so it takes a minute for one cycle. It's a sine wave that has a period of 1 minute. Now that's pretty much like the highest frequencies that they care about, the balance authority. A little faster, maybe 20 seconds, but So it's really, we want high gain from say here onwards. And let's just be conservative to begin with and just make high gain, well away from there. Okay? And this is mainly because, this is not a control course, and I want to make this easy on myself. All right? So if that's the case, so I want high gain over here, and I want low gain over here. Well, it's already going low. But I can get it with murder. I could just use an integral control. Make it easier myself. So, and it's got a, what's called a crossover frequency for all values of make, it looks like. Here's the control design. Well, actually, it's a second design. I did some crappy design last time. This is a little better. It's not great, but a bit better. So my first design is I'm going to set the crossover frequency to that value. I'll remind you what that is in a moment, okay? And make sure that I have reasonable phase and gain margins, and I'll define that as well. So to remind you of what these things mean, I've got 1, 2, 3 bits of jargon there. I'm going to have to go through, and I need pictures. I can't do this by definition. I can't do this, on the blackboard. But the main idea is this. I'm going to get rid of the phase for a moment. One more thing to remind you from last lecture. For this feedback loop that I showed you last time, the transfer function from the command input to frequency deviation is g over 1 plus g. Okay? And you get a pole when g equals -1. That's why -1 is an important thing. You get a pole when g equals -1. So if the magnitude of g equals 1 and the phase of g equals -180 degrees, that's a pole. And those are the two things you see in a Bode plot. You can see that's the absolute magnitude, not in dBs. In dBs that means 0. So you look at this value of 0. That's a crucial point. Because if the magnitude is 1 or 0 in dBs, and you find that the phase is -180, you use a pretty bad design. All right. So anyway, any design is going to look like that. Any design. So if somebody has done a design, a control design, and you want to ask them, what's your Bode plot of the closed loop system? It's called a loop transfer function. Once you've told your crossover frequency, there's a Bode plot. I designed it that way. I designed it so it's unity gain here, which means 0 dB, and I decided it goes down. Do you all know why it goes down? It was our original control objective.
High gain.
Yeah.
Oh, okay.
Yeah. I mean, we know over here we're going to have high gain. So I could fill in that Bode plot too. High gain over here, and lower, or moderate gain over here. So, you could say, well, why not have it go down? It'll come up again. Well, then I get another crossover frequency. I want one crossover frequency. Because it's like, here's where the danger lies. I can get into real problems with stability if I don't have things really under control here. Right? And so the original system, so we know that the plant is flat. The gain is just flat for low frequencies. And I know that this thing has just a linear slope. So you can guess that my design is just going to keep going. So there it is. You know what I mean? And at some point, what's that?
Slope also negative 20 dB per decade.
Yeah, the same slope, right? Because when you multiply transfer functions together and you look at the magnitude in dBs, you sum the Bode plots. And this thing has been normalized to be 0. It's a constant. So all we're seeing for low frequencies is the compensator, which has a slope of minus 20 dBs per decade. Right? Cool? All right. Okay, and then, when you look at this, well, it's going to go down further at some point because the plant does. Well, it looks like maybe we can just get away with murder. Let's just use integral control. Let's forget about the zero altogether and try it out. It's the first step, okay? So it makes things easier. So if we just forget about that, 'cause it looks like with this design we can get away with it. Yeah, we're going to introduce 90 degrees of phase lag, right? That's what I told you. I told you that the frequency plot is minus 90 degrees. But is that going to be so bad? I mean, we're I don't know. Zero there for the product. So we're going to set this. This will check through plots in a moment. I'll define what phase and gain margin is in plots in a moment. But we need okay, so we need the product to have zero in dBs. We need the product to have zero, unity gain at the crossover frequency. Again, I chose this example so that it would be easy. The plant already has unity gain at that frequency. I'll put an approximation there. It's maybe not exactly true, but. And again, through this very, very simple controller, it's just Ki over that. Okay, well, guess what? I mean, the magnitude of J is unity. That doesn't matter. And so I want Ki to be equal to omega C. Done. So there it is. There's our design. All right, let's analyze it. Let's go to MATLAB and type in numbers and see what happens. Is that clear? All right, my only objective is to make sure that I have set the crossover frequency as desired. And when you look at this, obviously these two things have to be the same. So it makes it really easy. Questions?
How did you make this approximation?
Well, it's actually, I mean, if you look at this right here, so we're looking at omega equals 0.1, right? And just check it out. If I go up and look at the, that's 0 dBs already, which means unity.
Okay, so
Yeah.
you're saying.
So this, I'm just saying this is 1 already.
Okay.
Yeah. Yeah.
So you derived that from the plot.
Just from the plot. Yeah, absolutely.
So in a situation where it's not at the same.
Yeah, then you have to go look at the Bode plot and see what the value is and take that into account. Yeah.
Is negative 180 just a scale frequency because that's where your poles are right there?
That's right there. It's that fear. I want not just to be stable. I want to make sure my closed poles are nowhere near the imaginary axis. You know, and so you want whenever the magnitude's 1, you have to make sure the phase is far from minus 180. All right? And that's yeah. All right, and 230. Cool. Shall we? All right. So there's the design. So as I told you, we've done some damage to the phase because I just use integral control. I'm adding negative 9 degrees everywhere, and so the phase, which was going down to minus 180, now goes to minus 270. But I also, this is my plan. I also added on a straight line. You know, the fact that it's integral control means this just keeps going down forever. So I've suppressed higher frequencies even more. So while before the gain was going down, you know, considerably, now it's shooting down much faster. So where that uncertainty lies, it's been flattened to death. And yeah, I mean, 20 dBs isn't that much, but at least it's small. Okay. So that's what it looks like in the blue curve. Again, is my design. It's the transfer function from balancing authority to frequency deviation times my PI, actually I controller. All right. All right. What you really do is this. Yep.
Can you go back to that?
Yeah.
So the blue line is your design, right?
Yeah.
So
it's
why is the
approximate.
phase at negative 90s?
Remember the. I've erased it now. Remember for the integral controller, we had this. The magnitude was decreasing, but the phase was minus 90. The PI control. The PI compensator. The PI compensator has this. PI compensator is a flat minus 90 forever. If it's just I, if it's just integral control.
So how did you calculate the dip? Is that just what?
MATLAB.
Okay.
In fact, I'm going to show you the commands in a moment.
Okay.
Yeah, so Bode and MATLAB gives this to you.
So then between the.
But this is just a constant offset. I could have done this just with an arts program just by moving it down 9 degrees because I'm just, yeah.
But, okay, so then in the region for the magnitude, the slope of that's also. Oh, no, I understand that part.
Yeah.
Because you want to lower the gain for the uncertainty.
Yeah.
But between the region, between the dotted lines, that's.
Well, I can explain that in a moment. No, between the. Well, that's because it's. This is just you take a. When you add on this Bode plot, which is just a straight line minus 20 dBs per decade, and you add that to the red curve, you get the blue curve. So the blue is the product of the two transfer functions. The blue is G. Okay. And so when the beauty of dBs is you add the Bode plots. And so if I take this red curve and add a straight line, I get something with slope minus 20 dBs per decade there. And out here it's minus 60 because the planet itself already had minus 40 dBs per decade.
Okay, so the slope of that line up to that point is negative 20 dBs.
Well, it goes down like that, minus 20 dBs. Something funky happens here, and eventually goes down minus 60 dBs because you've got 3 poles and no zeros. All right. And if I'd used PI, the phase would have eventually recovered here, and the slopes would have been the same at high frequencies. But I don't care about super high frequencies anyway. It's to me minus 80 60 dBs, that's 0. In my world, that's 0. Not to a physicist, but to a control engineer, that's 0. Okay, so here's what you do in MATLAB. So you go in, and you'll see some funny. You can look inside my life last night if you stare at these screenshots carefully. Not this one, but I did the same thing. Designed the PI compensator. We already defined this, the plant transfer function, and then you can type margin in MATLAB. So margin is a really useful command. And you type margin, and you get what I just showed you. Okay? But now let's slow down on this. It's really important. So first of all, 10 to the minus 1, that was my crossover frequency that I designed. You can see MATLAB agrees. MATLAB says, good job. It's telling me, well, I was off by a bit. It's telling me the crossover frequency is at 0.101.
This is the optimal.
No, nothing optimal. This is just
Wait, so what is this margin
I'm explaining.
value?
No, I'm explaining. I'm explaining. So the dashed line that MATLAB gives you from this command is the crossover frequency, and you can see that I'm off a little bit because I had an approximation right there. This wasn't exactly unity. It was off by I was off by 10 to the minus 2, but big deal. Okay, now the phase margin is how far I am away from this scary minus 180. So if this thing wasn't there, if it was there, I'd have a pole exactly on the imaginary axis at this frequency, because I would have phase minus 180 and a gain of 1 at a value j omega. That's bad. I've got a pole on the imaginary axis. So this is very nice. It says what I did what I said I was going to do. I made sure I had a really big phase margin.
So how does it know to check it at 0.101 radians?
It checks where the gain is unity. Yeah, that's the definition. So the definition of phase margin is you look at your loop transfer function, G. You look at where it's magnitude 0 dBs, and you check the phase, and you see how far am I away from minus 180. The farther where you are, it's a one big measure of robustness. But it's a lopsided view, because this is also important. You look at the frequency. Where is the phase minus 180? And so the margins command does that as well. It goes over and says, there's a frequency where the phase is minus 180, and it turns out to be at 0.383 radians per second. And then it goes up and says, how far am I away from being 0 dBs? And unfortunately, 13 is okay. 13 dBs is the distance, but not as good as I'd like. So, I'd rather, I don't know what 13 dBs is. It's maybe 7.
Yeah.
So if I cranked up my gain by 7, maybe it's a bit less than that. We'll see.
Do you want like a gain close to 0 or close to 1?
No. What do you mean by that?
You want to keep
Here's the gain. I mean, the gain is what do you mean?
It's saying at that frequency, the gain margin is 13.6, but you want the gain margin to be as close to 0 as possible.
No, infinity. Now, remember what we're talking about. Here's my closed loop system.
Oh, you want smaller.
Yeah, and a pole is when g equals minus 1. So, so magnitude is 1 or 0 dBs. The phase is 180. I sure as hell don't want a pole on the imaginary axis. And the farther, I want my poles to be far from the imaginary axis. And
so at negative 180, you want it as big as possible.
I want this to be far. So this says I could perturb the system a little bit. I mean, a little bit. 13 dBs is not small, but I could perturb it a bit, and I get a pole exactly on the geometric axis. And if I perturb it a bit more, I get poles in the right half plane. And so no matter what, it's unstable. Okay? So that's my margin to uncertainty there. And I don't like it. And I think the book's wrong. I don't believe that they just use integral control. I just don't believe it. And I've tried. I have friends at ISOs. They won't. It's so hard to talk to people in the control room, because there's a lot of they've been doing it for their daddy did it. There's sort of dogma passed down, and there's a lot of hacks that go on. So people don't really want to talk. It's hard to get to the inside. So So anyway, so I think that if I was actually to be put to work on this, I probably would use a proportional control, and I'd do some more things as well. I'd have to find out how much uncertainty there really is in this region, and based on how much uncertainty there is, I could refine the design and get a better gain margin, and maybe get this crossover frequency more to the right. Because as we're going to see, we don't really have enough bandwidth to make PJM happy or ERCOT. We're about to see that. It's actually the design does not have high enough gain at the frequencies I care about. Okay.
Wouldn't you want the gain to be 1 at lower frequencies?
No, I want massive gain. Oh, to the phase margin. No.
So you can have the phase margin.
No. Remember my goal. I want to reject disturbances. So I need GC big to reject disturbances. So ideally, for disturbance rejection, I want that crossover frequency to be way over here to the right. If I want to reject a huge range of disturbances. If I'm completely terrified of stability, I want to move this way to the left, maybe, because then I'll have huge gain margin and phase margin. You know, but you could be more delicate and try to shape the Bode plot to have, to push this as far as you can while maintaining reasonable gain and phase margin. And that's a big job. You might have a fairly complicated controller. It might be, it'll probably be a combination of PI and what's called a lead controller. That's probably what I would use. But that's a control course. You'd have to take a whole course. But at least it's enough to get you ideas. Is that clear, though? We've got these two competing objectives, trying to push out disturbances but also have stability. Naturally, those are conflicting. All right. So there's the whole thing. So here's actually what the whole diagram would look like. You've got, this is just another way of expressing what we had before. So I've broken up, you notice I've got an STG plus 1 and STG plus 1 there. Those cancel out. The dynamics from the balancing authority to the deviation in frequency. And grid disturbance to this had that 0. So this is just a nice way of expressing everything. And we designed this compensator. The reference signal again is 0 because we would like to regulate it to 0. And we came up with this very cheap design, something you could do in 15 minutes. All right. And so those are the things we use. I'm just reminding you. So, there it is. I want to show you how to this beautiful gift from God meaning MATLAB, called Simulink, and show you how you can play with it. So I sent you this today. So MATLAB lets you just drag and drop transfer functions. There's the grid. There's my compensator. There's noise from nature. And you can actually get noise from nature. You can have it input samples of noise from solar or wind or whatever you like. And there's a scope and so forth. So it takes about 10 minutes to do this. And here's where you can really start laughing at me. Like, that's 10:47 p.m. last night. And my battery power looks like it's 50%. All right, so there it is. And I had a lot of trouble with this because I was trying to shape the noise so it's consistent with what you would see at PJM, and I kind of failed. Anyway, so this is just 10 seconds. So the variability of noise is really not that great. I mean, this is higher frequency than you'd see in real life. And the red is the disturbance, and the blue is my frequency deviation. And you can see I'm not doing that great a job, but I'm canceling out a lot of that red stuff, but there's still a lot of blue left over. All right? Okay. All right. So what about cranking up the gain to 10? So it was 0.1. What about 10? And it goes this is 6 seconds, it goes wham, and it just blows up. So it's totally unstable. All right. So definitely the gain margin is less than 10. And here's a more realistic experiment, not in terms of frequency content, but one of our goals was really rejecting really low frequency disturbances. Here's a disturbance with a constant value 1 included. So that could be 100 megawatts if you like. Okay. and it's positive, which means you've got 100 megawatts of extra generation, a generator turned on and stayed on. It's not very realistic, but so you see, because of the fact there's a startup, you get a big transient in the frequency, but then it settles down, and you see you eject the DC component of the disturbance perfectly, but you're letting a lot of the high frequency stuff come in, and that's about a minute and a half, 100 seconds. That's way too much, So this design there's not enough bandwidth in this controller. It should have a higher gain over a larger frequency range to be able to switch this down further, the higher frequency part, right? And here's where things get really depressing. Shall I? Oh, that's 5. That's a mistake. Oh, wait, I better double check. I have to check my code. Now I'm not sure. It says 5 there, but I think it's only 0.5. I think that's a typo. I'll correct and get back to you. I wanted to see numerically where the system would become unstable. It wasn't 5, it was 0.5. So my gain margin is only 5, or less than 5. I'll double check. This could be wrong, but you see that oscillatory behavior. We've got poles in the right half plane, but very close to the imaginary axis. So that's a bad design. That's a really bad design, where I've actually increased I don't think it's not 5, I'll check. But by increasing the gain, I end up moving the crossover frequency. And so I end up in that area with a lot of phase lag. So it wouldn't be unstable if we weren't doing so much damage with integral control. We're introducing all this phase lag, which we don't need.
Doesn't 5 make sense though? Because this is in dB, right?
No, 5. No, because I went from 0.1 to 5.
Oh.
Yeah. 0.5 would make 0.6, something like that would make sense. Yeah. So I'm pretty sure it was 0.5. I'll go check my code. But it just shows that they have a big job to do. And so can you imagine how they feel in New York State, New York ISO, when the Public Utilities Commissioner, Audrey Zilberman, is saying, we're going to have transactive control, and every homeowner is going to ramp up and down their power consumption in response to grid signals. And these poor grid operators have dealt with this. And they're really worried about their design. Grid operators are scared to death in the US because there's so much talk about revolutionizing the grid. And yet, these things happen. I can show you plots of this. I think I already have, but I'll show you again. So anyway, keep this in mind as we go forward. Control is a subtle problem.
Has control design not changed in the past 50 years then?
Oh, well.
For grid control?
No, it hasn't. It hasn't at all. They've come up with...
That's kind of disturbing.
Well, no, it's just decentralized control is hard, this is the fact that the things you can't blame the grid operators. The fact that we have a system with so much uncertainty means you've got to be conservative. So if somebody comes along and says, hey, I've got a new approach to optimal blah, blah control, they'll have to ask you, well, how robust is it to uncertainty and phase and gain and blah, blah, blah. And so it's a difficult thing.
Do you think there would be a way to normalize disturbances?
What?
Maybe having